So I'd like to illustrate the process of changing the order of integration using this example that you'll be familiar with from your homework. So the point is, this double integral is too difficult to do as it stands, and the inner integral is with respect to x, but e to the 3x minus x cubed is something we don't know how to integrate with respect to x. But if we're lucky, this may be easier the other way round. Certainly if it was dy dx, integrating this with respect to y would just be a matter of multiplying by y. It would only be when we get to the outer integral we'd have to worry whether we can actually do it. But let's see what happens. Now, we're given the limits here, dx dy. We want the limits for doing this dy dx. There's no simple way to look at this and get that. What we must do is to draw a picture of the region of integration. So using the limits, we have y on the outside, and this is y equals 0 and y equals 1, bounding the region. So let's put those in as y equals 0 and y equals 1. Now moving in, we've got x equals 0 and x equals root y, bounding the region. So here's x equals 0, and let's see, x equals root y is like y equals x squared, so that's going to look like this. And I think, yeah, it goes through the point 1, 1 here. Okay, now the region of integration then is trapped between y equals 0 and y equals 1. And then for any y value that we stop at in between 0 and 1, on that horizontal line corresponding to that y value that we've stopped at, the interval of x values that's inside the region is from 0 to y. So yeah, this must be the region. We're going from x equals 0 to x equals root y. Now we've got to reverse this process, but in such a way that we end up with the limits for the dy dx integral. Now we can do this purely from the picture. If we'd been given the region to begin with rather than these limits, we could work this out just from the picture. So let's delete the original limits. Now, obviously it's the same integrand, but we're going to do this dy dx. Now, how do we use this picture of the region, to get the new limits? Well, okay, it's the standard process of given a region, getting the limits. So given this region, now on the outside we've got dx, so we want x limits here. So rather than a pair of horizontal lines bounding the region, we want a pair of vertical lines bounding the region, and that's going to be x equals 0 and x equals 1. Right, x equals 0 forms part of the left-hand edge of the region, and x equals, when we bring in the line from the right, x equals 1 is the first time it touches the region. So I can put those in then. So now we've got a vertical line sweeping across. X equals 0 to x equals 1 and all values in x values in between, and if we stop somewhere in between at some fixed x value, then along that vertical line we want to know which part of that vertical line is inside the region. what's the y value, what's this interval of y values that's inside the region. The lower limit is whatever y is here, and the upper limit is whatever y is here. But as we enter and leave the region, we're crossing boundaries of the region. So this is a case of expressing the equations of these boundary curves, boundary line, that one, in the form y equals something. Now the upper one's easy. At the upper end, we're just crossing the line y equals 1, and whenever we do that, y is 1, so that's the upper limit. As we enter the region, we're always crossing the curve x equals root y, but in the form y equals something, that's y equals x squared, so that's the lower limit. Okay, well now we're ready to do the integral, having set it up like this. Let's see if this does make it any easier. Okay, well, integrating with respect to y, as I anticipated, it is trivial for this because the integrand only depends on x, so integrating that with respect to y, we just multiply by y, treating this integrand as a constant. And we've just integrated with respect to y, so these limits here are to be plugged in for y. And when we do that, we'll get a factor of 1 minus x squared. Now this is the thing we had to worry. I knew I'd have to worry about this eventually. What integral dx do we end up with at this point? Well, whereas we couldn't integrate the e to the 3x minus x cubed dx, with this extra factor of 1 minus x squared, this is just what we need to be able to do this now. Now, it may look like a product that you try to do by parts or something, but just look at it. This is right for a substitution because we've got a kind of inner function here. And if we differentiate this with respect to x, then up to a scalar multiple, we actually mop up this factor. So what I'm saying is, let's let u equal 1 minus x squared, and then u equals 3x minus x cubed, and then du is 3 minus 3x squared dx. And so what we've got here is, well, we've got e to the u. Now this whole 1 minus x squared dx is a third of du. And now when x is 0, u is 0, and when x is 1, u is 2. So, all in all, we've got a third of the integral. Yeah, so I hardly need to finish this off, do I? So this is a third of integrating e to the u, we get e to the u. So this is a third of e squared minus 1. So yeah, it turns out that changing the order of integration turned an integral that we couldn't do into an integral that we could do. So that was definitely a good idea. Okay.